Welcome to Friday Happy Math Hour. Today we're going to cover basic matrix operations and inverses. So these are the topics that I'm going to cover today. To start off, they're going to be real life examples. Determine dimensions, which is the size of a matrix. Matrix addition, matrix subtraction, the scalar multiplication, and applications problems. And then the second part, I believe, the second part is going to be matrix product and inverses, which is matrix multiplication, the identity matrix, and inverse matrices. Okay, so let's begin with a real life example. Okay, so before we start, we have to know some of the definitions, and so students can know what they mean when they're asking questions on assignments. Matrices are important in the fields of management, natural sciences, engineering, and social science as a way to organize data. Example number one here. Furniture manufacturing. It states, the Easy Life Company manufactures sofas, armchairs, in 3 models. Model A, B, and C. The company has regional warehouses in New York, Chicago, and San Francisco. In its August shipment, the company sends 10 Model A sofas, 12 Model B sofas, and 5 Model C sofas, and 15 Model A chairs, 20 Model B chairs, and 8 Model C chairs to each warehouse. Okay, now, so all this data might be organized by listing them as follows. Okay, so for example, for sofas, right, we have 10 Model A's, right here from the beginning. Let's go here to the word problem. Here we go, 10 Model A's, 12 Model B's, and 5 Model C's. And then for the armchairs, right, for the chairs, it's going to be 15, right? So it's 15 Model A's, 20 Model B's, and 8 Model C's. So this data may be organized, perhaps in this fashion here. Alternatively, we might tabulate the data. This is like an invoice, right? This is the furnitures, right, which is sofas and chairs. This is the models, A, B, and C. So there's 10 Model A sofas, 12 Model B's, and 5 Model C's. And same thing with the chair. There's 15 Model A's, 12 Model B, and 8 Model C. So it can be organized in this manner, or also in this manner here, like a tabulated data. And also it can be done in a matrix. Okay, for example, this is in a matrix. The rows refer to the furniture, and the columns refer to the model, which is A, B, and C. For this chapter, or for this matrices, everything's going to be done in matrices. Okay. So example 1 can be written in all these 3 forms, but we're going to concentrate on matrices in this form here at the bottom. Okay, so let's get some definitions and how matrices operate. For example, matrix A, and we have matrix B. If you notice, the uppercase letters represent the name of the matrix, okay, or the matrices. You see, they're uppercase, and the lowercase are called the elements or the entries. Okay, for example, A11, A12, and so forth. Now let's see what it means by A11 and A12. Okay. You see, for example, these are my rows. These are my rows, and these are my columns. Okay, up and down. So for example, the position of an element, okay, the lowercase letters are elements or entries. Okay, now A11 means it's going to be the 11th position is in row 1, column 1. So the 11 means row 1, column 1. A14 means, right, row 1, column 4. You see, the first number are the rows, the second number are the columns. Okay, now A23 will be the same thing, right? Second row, third column. Now let's do an example here. what is the position of the following elements? For example, A13, right? A means the first row, third column, which will be where the number 3 is. A24 is the second row, and the fourth column, which will be the position, will be where the 8 is. Okay, so it's very crucial to know the positions, because when you add and subtract or do operations on matrices, you have to go by the positions. Okay, the positions is a key concept to know. Okay, now comes the dimensions, or the size of a matrix. It's going to be rows by columns. Number of rows by number of columns. Example here, right? So this, for example, right, there's going to be 2 rows and 4 columns. So the dimension or the size of this matrix is a 2 by 4 matrix. Example 2, determine the dimensions of the matrices. For example, okay, let me go back real quick. For example, this matrix here on the left, you have 3 rows, 1, 2, 3, right? And 3 columns, 1, 2, 3. So that's going to be a 3 by 3 matrix. The matrix in the middle is going to be 3 rows, right? 1, 2, 3 rows and 1 column, so it's going to be a 3 by 1. The matrix on the right is going to be 1 row, right? It's only 1 row and 3 columns, so it's going to be a 1 by 3. Now, for like a self-check, determine the order of the matrix. So how many rows do we have? 1, 2, 3, 4. So it's going to be a 4 by 1, 2, because we have 2 columns. It's going to be a 4 by 2 matrix. Okay, now matrix operations. So it's crucial to know the order or the size of the matrix, because when you add and subtract matrices, they have to be the same size. So that's crucial. Okay, for example, again, we go back to matrix A and matrix B. So in order to add and subtract matrices, the matrix must be the same size as I mentioned earlier. So A plus B, right? We're going to get the position on matrix A, the first row, first column, plus the B matrix on the position of, the position of the B matrix has to be first row, first column. So it's going to be A11 plus B11, A12 plus B12, A13 plus B13, and so forth, right, until we get to the end. And then, right, and then it's going to be A21 plus B21, and so forth, right? And you keep going all the way till we get to the end. Okay. And again, they have to be the same size in order for you to do the operation. Now, here's the definition. Matrix addition, the sum of 2 m by n matrix, right? These are the size, m by n, for matrix X and Y. M, the size of the matrix, a matrix X plus Y, in which each element is the sum of the corresponding element of X and Y. This is really what it means, right? So for example, if we have 2 matrices, this can be matrix A, B, or X and Y. It doesn't matter, right? The uppercase letter represents the matrix. So what we have to do, we have to add the first row, first column on matrix A, plus the first row, first column on matrix B, and so forth. That's what this definition means here. And it's also the same thing for subtraction. Okay? So I'm going to do an example of addition and then subtraction. So for example, example number 3. Here is a list of matrices from A all the way to D. So before we start doing any type of operations, let's find the size of the matrix. So for example, matrix A is a 2 by 3 matrix. And matrix B is also a 2 because it has 2 rows and 3 columns, so it's also a 2 by 3 matrix. Matrix C is a 2 by 2 because it has 2 rows and 2 columns, 2 by 2. And matrix D also is a 2 by 2 matrix because it has 2 rows and 2 columns. So now let's add matrix A plus matrix B. Can we do the operation? Sure we can, right? Because they're both the same size. So what we're going to do is going to be 1 plus 8, and then negative 3 plus 0, and 2 plus 1. And then it's going to be 2 plus negative 1, 2 plus 3, and negative 1 plus 4. So then we simplify it. So it's going to be 9, it's going to be negative 3, it's going to be 3, it's going to be 1, 5, and 3. So this is the answer of the operation of matrix A plus matrix B. This step here in the middle, you don't have to do it that way if you don't want to. This is just to show you what we do, right, to find the answer. You can just go 1 plus 8 is 9. Negative 3 plus 0 is negative 3. 2 plus 1 is 3. 2 plus negative 1 is 1. 2 plus 3 is 5. And negative 1 plus 4 is 3. Right? You can do it either way, but here I'll show you I'm going to show you by the definition how to add them. But like I said, this step can be skipped if you want. You can go straight from the addition all the way to the answer. Okay, now, how about C plus D? Matrix C is a 2 by 2, and matrix D is a 2 by 2. So the operation can be done. And again, similar manner, right? So it's going to be 5 plus 2, 1 plus negative 1, negative 4 plus 9, and 3 plus negative 7. And now, right now, it simplifies. It's going to be 7, 0, 5, and negative 4. That's my answer. How about A plus C? If we notice, A matrix is a 2 by 3, and the C matrix is a 2 by 2. So that cannot be done. So it's not possible because they have to be the same size. Okay, not the same size. That's the reason why. Now, example 4. Okay. Again, 2 by 3. 2 by 3, right? Because first we have to put the same matrix, and I believe they're the same size of matrix and the same elements in each matrix. Now, let's subtract. So A minus B. So it's going to be 1 minus 8, negative 3 minus 0, 2 minus 1, 2 minus negative 1, 2 minus 3, negative 1 minus 4. Now to simplify, it's going to give us negative 7, negative 3, positive 1, positive 3, negative 1, and negative 5. That's the result of matrix A minus B. Now let's try C minus D. It's going to be 5 minus 2, 1 minus negative 1, negative 4 minus 9, 3 minus negative 7, and here's my result. 5 minus 2 is 3. 1 minus negative 1 is positive 2. Negative 4 minus 9 will give us negative 13. And 3 minus negative 7 will give us a positive 10. So this is my result. And again, A minus C is not possible again because matrix A is a 2 by 3 and matrix C is a 2 by 2, not the same size, so it cannot be done because not the same size. Okay, now comes a scalar multiplication. The product of a scalar K and a matrix X is a matrix K times X in which each element is K times the corresponding element of X. Let's do an example so this can make more sense. Okay, for example 5, matrix X is given, right? And it's a 2 by 3 matrix. We have 2, 0, 5, 4, negative 2, and negative 3. So 6 times matrix X is going to be 6 times matrix X. So we're going to multiply the scalar times every element in matrix X. So it's going to be 6 times 2, 6 times 0, 6 times 5, 6 times 4, and 6 times negative 2, and finally 6 times negative 3. Now we do is simplify. So it's going to give us 12, 0, 30, 24, negative 12, and finally, negative 18. That's my result of multiplying a scalar times a matrix. Okay, now let's find negative x. Negative x is like negative 1 times x, right? So negative x is negative 1 times matrix x. So it's going to be negative 1, right? In other words, you don't have to multiply it, right? Because if we multiply it, right, all we do is we're going to switch the signs on all these elements. Because negative times a positive, right, will give you a negative 2. So in other words, all we do when you have a minus a matrix, all these elements in matrix X, we're going to switch signs because negative 1 times 2 is negative 2. Negative 1 times 0 is 0. Negative 1 times 5 is negative 5. Negative 1 times 4 will give us negative 4. Negative 1 times negative 2 will give us a positive 2. And finally, negative 1 times negative 3 will give us a positive 3. So in other words, all we do is switch all the signs. That'll be much quicker. Okay? So now let's do example number 6. They give us two matrices, matrix A and matrix B, and they're both the same size, right? So let's do number 1 is going to be negative 4A, number 2, 5B, and number 3, we're going to add what we got from number 1, which is negative 4A, plus what we got for number 2, which is plus 5B. Okay? So let's see. So number 1, negative 4A, I'm going to multiply negative 4 times every element in matrix A. So again, negative 4 times negative 2, negative 4 times 0, negative 4 times 5, and negative 4 times 3. And again, like when we're adding, right, we can skip this step here, but I just showed you guys so you know exactly what we're doing here. We can just go from the negative 4A, from negative 4 times matrix A to the result. Negative 4 times negative 2 will give us an 8. Negative 4 times 0 will give us a 0. Negative 4 times 5 will give us a negative 20. Negative 4 times 3 will give us a negative 12. So that's my result of negative 4 times matrix A. Now let's do number 2. The scalar 5 times matrix B. So we're going to multiply 5 times every element in matrix B, which is 5 times 0, 5 times 2, 5 times 4, and 5 times negative 6. So 5 times 0 will give us 0. 5 times 2 will give us 10. 5 times 4 will give us 20. And 5 times negative 6 will give us negative 30. So this is my result of the scalar 5 being multiplied by matrix B. Now let's add negative 4A plus 5B, right? So I already did the work here, right? So this is negative 4, which is 8, 0, negative 20, negative 12, plus 5B, right? I already got the answer on number 2 there. So I'll just bring it over. Now we're going to go from, we're going to do what we did at the beginning, right? When we added matrices. So it's going to be 8 plus 0, 0 plus 10, negative 20 plus 20, and negative 12 plus negative 30, which is going to give us 8, 10, negative 20 plus 20 will give us a 0, and negative 12 plus negative 30 will give us a negative 42. That's my result. Okay, now let's go back to the word problem. This is a word problem from the beginning, right? Okay, again, recall example. Furniture manufacturing. It says the Easy Life Company manufactures sofas and armchairs in 3 models, right? It's the same example as I believe the second slide. But we're going to add a little bit extra on how to actually use matrix to solve word problems. The company has regional warehouse in New York, Chicago, and San Francisco. In its August shipment, the company sends 10 Model A sofas, 12 Model B sofas, and 5 Model C sofas, and 15 Model A chairs, 20 Model B chairs, and 8 Model C chairs to the warehouse, to each warehouse, right? Which is in New York, Chicago, and San Francisco. So this is how, this is what's being sent, right? It's going to be, right? We have 10, 12, 5, 10, 12, 5 for the sofas, and 15, 28 for the chairs. Okay, now, during August, the Chicago warehouse of the Easy Company shipped out the following numbers of each model, which the entries in the matrix have the same meaning as are given earlier, right? So in other words, right, so this was sent to Chicago, right, because the 10, 12, 5 sofas and 15, 20, and 8 chairs were sent to each city, New York, Chicago, and San Francisco. That's why they're going to put C, capital C, right, which is matrix that goes to Chicago. And K means, right, that these were shipped out. So in other words, how are we going to use a matrix to solve by problem by using matrices? So what was Chicago's warehouse inventory at the end of September? Take into account only the number of items received and sent out of the month, right? So this was the model received was C, and the model shipped out was K, right? So then, to see how many models are left in the warehouse, we're gonna subtract what was shipped in and what was shipped out. So it's gonna be 10, right? 10 minus 5 is 5. 12 minus 10 is 2. 5 minus 3 is 2. 15 minus 13 is 2. 20 minus 12 is 8. And 8 minus 8 is 0. So what was left? There were 5, right? Remember, the first row represents chairs, so there's 5 Model A chairs that were left, 2 Model B chairs. Sofas. Again, the first row are sofas, and the second row is chairs. So there's 5 Model A sofas, 2 Model B sofas, and 2 Model C sofas left, and 2 Model A chairs, 8 Model B chairs, and there's no Model C chairs left because they all went out. Okay, now we're doing the product of matrices. This is very important information, right? Multiplication of matrices can only be done under the following conditions. For example, when we add and subtract matrices, right, they have to be the same size. That's not really the case for multiplying matrices. Let me show you what I mean by that. If matrix A, right, this is matrix A. Matrix A says an n by n matrix. This can be any numbers, right? But matrix B has to be an n by p. In other words, the two in the middle must be the same, must match in order for you to do the operation. If these don't match, then it cannot be multiplied. And the answer is going to be the outer. It's going to be an m by p matrix. Okay, let me show you an example so you guys can know what I'm talking about. Okay, here's a question. If the size of matrix A is a 2 by 3, then matrix B must be a what? Remember, these must match. So matrix B must be a 3 by something. It doesn't matter what the other number is. It has to be a 3 by a number. Number can be any number in order for you to do the operation. And the answer will be a 2 by whatever this number is. In other words, remember, the 2 in the middle must match. Okay, let's do one. Example 7. Given the following matrices, state whether the matrices can be multiplied. Matrix A is what? A 2 by 3. Matrix B is a 2 by 2. Matrix C is going to be a 3 by 2. Again, this is a 2 by 3 matrix, right? This is a 2 by 2. And C is a 3 by 2. Okay, now, can we multiply A times B? Let's find out. So A is a 2 by 3 and B is a 2 by 2, right? So the 2 in the middle, right, the inner numbers do not match. So no, it cannot be done. No match. Cannot multiply. How about B times A? B is a 2 by 2 and A is a 2 by 3. You see the two numbers in the middle? They match. So yes, it can be done. And the solution will be a 2 by 3 matrix. How about A times C? A is a 2 by 3 and C is a 3 by 2. So yes, again, yes, it can be done because the two numbers in the middle match. And the answer will be a 2 by 2 matrix. Now, let's put that concept into action. Okay, now example 8. We have a matrix is a 2 by 3, and the elements are 2, 0, 5, 4, -2, -3. And matrix B is a 2 by 2, right? Which is the first row is a 1, 0 in the elements, and row 2 is 4, -2. So B times A, right? So B times A, right? Yes, it can be done, right? We can actually multiply it because it's a match. And the answer is going to be a 2 by 3 because those are the outer numbers. Right, so this is going to be the answer. So, okay, so let me show you what we're going to do here. Okay, step 1. We're going to multiply, right? That's why I color-coded them. I'm going to multiply every row on matrix B times every column on matrix A. You see, that's why I'm going to multiply the blue times the red. This is for step 1. Okay, so here we go. And then after I'm done with step 1, right, then I'm going to be multiplying the first row on the first matrix, which is B, times the second column and the third column and so forth. Okay, now, so it's going to be 1 times 2 plus 0 times 4. 1 times 2 is 2, 0 times 4 is 0, so 2 plus 0 is 2, so 2 is my first element for the solution matrix. Then we go to step 2 then. Step 2, we're still going to keep the same row, right? We're going to keep the same row because we're not done yet. The first row must be multiplied times every column on matrix A. So now I'm going to switch the column that I'm going to multiply to the second column, which will be in red. So again, I'll repeat the process. So 1 times 0 plus 0 times -2. We get 0 plus 0, so the answer will be 0. So 0 will be in the position of the first row, second column. Now the third step. We still keep we still have the same row because we still need another column to multiply by. That's why the last column will be in red. So 1 times 5 is 1 times 5 is 5, plus 0 times -3 will give us a 0, right? So this will be 5 plus 0. The answer is 5. So the 5 goes on the first row, third column position. Right? Because there's no more columns to multiply by, right? There's no more columns. So that means that we're done with the first row, right? Because there's no more columns to multiply by. So now we go to the second row. So step 4, right? I'm going to switch the color that we're multiplying to the second row because now I need to multiply the second row times every column. So I do the similar process as I did for the first 3 steps. Okay, so it's going to be 4 times 2 plus -2 times 4. So it's going to give us 8 plus -8, which will be 0. So 0 will be on the second row, first column position. Now let's do step 5. We got one right. So again, now we're going to be multiplying by the second column. So 4 times 0 plus -2 times -2. That will give us 0 plus 4, which the answer will be 4. And again, the 4, the element 4, which is the answer for this particular step, is going to go on the second row, second column position. And finally, right, I'm going to multiply the second row times the last column, which is column 3. So 4 times 5 plus -2 times -3 is going to give us 20 plus 6. The answer is 26. So this is my solution. Okay, that's my solution. And that's how we multiply matrices, the concept of multiplying matrices. Okay, now let's move on. This is called the identity matrix. Okay, now recall from section 1.1 that a real number 1 is the identity element for multiplication of real numbers. For example, for any real number A, right? A times 1 or 1 times A will always give you A. For example, what's 1 times 1? What's 3 times 1? The answer is 3. What's 1 times 3? The answer is 3. So 1 is considered the identity element for multiplication in real numbers. Okay, now in this section, an identity matrix, like an identity element, is going to be I, which stands for identity. So here we go, right? So for example, matrix A, right? If we multiply by the identity, it's going to be A, the matrix A. A times the identity equals to identity times A equals to A. Here's what it means by the identity matrix is a square matrix. For example, if it's a 1 by 1 matrix, the matrix is 1. If it's a 2 by 2 matrix, the identity will be 1, 0, 0, 1. If you notice, all the columns diagonally have to be 1s. For a 3 by 3 matrix, it's going to be 1, 0, 0, 0, 1, 0, and 0, 0, 1. Again, all the diagonal elements have to be 1s. And so forth for a 4 by 4, 5 by 5, and so forth. Okay, let's do an example here. Example 9, you multiply matrix A. Here, this is a concept. Hey guys, when it comes to the concept, they or to prove stuff, they always use letters. They don't use no numbers because it's proving for any real numbers or any real elements. So matrix A, right, is equal A, B, C, and D. So the identity must be a 2 by 2 matrix, which would be 1, 0, 0, 1. Okay, now here, guys, I'm going to prove it to you that if I multiply A times its identity, it's going to give us the same matrix A. Okay? Here we go. Again, step 1, let's do what we did earlier. So that's my matrix A, B, C, and D, and that's my identity, 1, 0, 0, 1. So again, step 1, I'm going to multiply A times 1 plus B times 0. It's going to give us A plus 0. The answer will be A. Okay. Now, step 2. Repeat the process as before, right? I'm going to multiply the first row times the second column, which will be in red, the 0, 1 here. So A times 0 plus B times 1 is going to give us 0 plus B equals B. So B will be on the second row, second column. Right, so we're done right with the first row because there's no more columns to multiply by. So now it's going to be the second row that we're going to change colors, right? Because we're going to be doing the second row times every column. So it'll be column 1. So C times 1 plus D times 0, which will be C plus 0. The answer is C. So C will be the second row, first column. And lastly, step 4, we're going to multiply the second row times the second column, which is in red. So C times 0 plus D times 1, which will be 0 plus D equals D. You see, we get the same matrix when we multiply by the identity. I believe some of your homework problems are going to be the same way, right? So if you multiply A times the identity, will just be the matrix A. So you don't even have to show the work, right? Just it's like multiplying 9 times 1. 9 times 1 will just be 9. So here, guys, like multiplying matrix A times the identity will just be the same elements in matrix A. Okay, now inverse matrix. Inverse matrix. Okay, recall that for every non-zero real number A, the equation AX equals to 1 has a solution. Namely, because we multiply by the reciprocal, which is the inverse. The inverse is a reciprocal of any number. For example, if you have A, right, any number A, the reciprocal will be 1 over A, which is the inverse. Okay, similarly, for a square matrix A, we consider the matrix equation matrix A times X equals to the identity. The equation does not always have a solution. But when it does, we have the special terminology. If there is a matrix, inverse matrix A, right? So A times its inverse must equal to the identity. The inverse is called the inverse matrix. Okay, let me show you an example so the definition will make more sense. So example number 10. It says given matrix A and matrix B as follows. Determine whether B is an inverse of A. Okay, so they're saying here that B, determinant B is the inverse of A. So what do? We're going to multiply A times B. And the solution equals to the identity, which will be 1, 0, 1, 0, 0, 1, then it is the inverse. Okay, now here, I believe I didn't show the work here, guys, but if you follow the same concept as before, when you multiply, it will give you the identity matrix. So the answer is that B is the inverse of A. Okay, maybe for next time, I will show the work, okay? And also, guys, all these matrices can be plugged in a calculator, but it has to be a TI-83, TI-84. I always show my students how to do it also in the calculator because it's always good to check their work. And I also tell them that, but to get credit on an exam, that they have to show me all the correct work. But with the calculator, guys, it's kind of simple procedure. Once you know it, you can get the answer within seconds, depending how fast you can punch in the entries on the calculator. Okay. So here A times B does give you the identity matrix. So B is an inverse of A. Okay, now if matrix A has an inverse, then A and the inverse must equal to the the A and the identity must equal to the inverse, all right? So here's how we do this one. I'm going to put matrix A, which is 1, 1, 4, 2, 6, and then I'm going to put the inverse. So here, guys, we're going to follow the Gauss-Jordan method of what we learned last week, right, from 6.2, and we're going to have to send, this side has to be equal to 1, 0, 0, 1, and then whatever is in this side will be the inverse. Okay, so if you plug that in the calculator, guys, this is what you have. So this is my inverse. Okay, but how do we get it? Okay, right, this is my inverse. How did I get the inverse? Okay, here we go. Here's a work by using the Gauss-Jordan method. Remember, guys, this is row 1, this is row 2. So I'm going to multiply, right, because this has to be a 0, right? But remember, this is my goal. The identity must come to the left side. And then whatever is on this side, on the right side, will be the inverse. So the first step is that the 2 must be a 0. And I explained this last week when I was doing the Gauss-Jordan method. So that 2 must be a 0, right? So I'm going to multiply -2 times row 1 and add it to row 2. And remember, as we did last time, if we use for step 1, we keep row 1. So here's my work. -2 times row 1 is going to be -2 times 1, 4, 1, 0. So after I execute that operation, right, it's going to give us -2, -8, -2, and 0. Then we're going to add it to row 2. Row 2 is 2, 6, 0, 1. So after we execute the addition, right, we're going to get 0, -2, -2, and 1. So that's my new row 2. If you notice, right, I'm done with the first step because that's already a 0. My second step is that the 4 must be a 0. So I'm gonna keep row 2 how it is, right? And then if I multiply +2 times row 2 and add it to row 1, it guarantees that the 4 will be a 0 because it's going to be eliminated. Okay, and here's my work. And again, guys, I color code everything. This way, students can see each required step. So 2 row 2 equals to 2, right? Times row 2, which is 0, -2, -2, 1. So after I do the operation, I get 0, -4, -4, 2. I'm going to add it to row 1. Row 1 is 1, 4, 1, 0. After I do the operation, it's going to give us 1, 0, -3, 2. You see, so now, guys, the only thing that we need is that this has to be a 1, right? On the second row, second column, that must be a 1. The -2 must be a 1. So how do we convert that? We multiply the whole matrix times -1/2. So -1/2 row 2, right? So -1/2 times 0 will give us 0. -1/2 times -2 will give us +1. -1/2 times -2 will give us +1. and negative 1/2 times 1 will give us a negative 1/2. If you notice, guys, we don't get no fractions until the very, very end if you do it this way. So this is my inverse. Okay? Okay, now, there's a different formula to find the inverse on a 2 by 2 matrix only. This formula only applies if the matrix is 2 by 2. If the matrix is 3 by 3 or 4 by 4 and so forth, this matrix cannot be done. Okay, so here's the formula to find the inverse matrix on a 2 by 2 matrix, right? This is matrix A. This is how you find the inverse. You're gonna use, I believe this is called the determinant, right? You multiply A times D minus B times C. And then what happens here, guys, you're gonna switch matrix A and D. I mean elements A and D. So the A goes to the position of D, right? A goes to the position of D, and then for B and C, all you do is switch signs. So this is my setup. Okay, now, example 11, find the inverse of matrix A. Right, that's matrix A. And I believe it was the same matrix that we did earlier with the Gauss-Jordan method. So remember, this is A, this is B, C, and D. So it's going to be 1 over 1 times 6 minus 4 times 2. And then remember, the 6 and the 1, the A and the D switch places. So it's going to be 6, negative 4, negative 2, and 1. Because for the B and the C elements, all you do is switch the signs. So I repeat, you switch elements A and D, and for elements B and C, all you do is switch the signs. So here, right? So this will be 1 over 6 minus 8. It's going to give us negative 1/2. So I'm going to multiply negative 1/2 times the elements on the corresponding matrix, which will give us negative 1/2 times 6 will give us negative 3. Negative 1/2 times negative 4 will give us positive 2. Negative 1/2 times negative 2 will give us a positive 1. And negative 1/2 times 1 will give us a negative 1/2. So that's my inverse. Okay, let me go back. So this is my inverse, guys, right? And we got the same thing as what we did earlier. Okay, now comes the inverse of a 3 by 3 matrix. Okay, there's no formula like the previous slide for a 3 by 3 matrix. You have to do it by using the Gauss-Jordan method. Okay, so this is matrix A, and this is my identity. So again, right? So again, here, guys, remember how we did it last week on the Gauss-Jordan method? I believe I did 2 examples. So here, where the 2 is, which is second row, first column, has to be a 0. The row, first column, so the 2 and the 5 must be zeros. Okay, so again, so step 1, right? So this is going to be my answer by using the Gauss-Jordan method, right? This is my inverse on the right. So now, how did they do it? Okay, so again, here's my setup again, right? So here we go. This requires, right, this was step 1. So I'm going to make the 2 and the 5 zeros. So step 1, we're going to keep row 1. So the second row has to change because the 2 has to be a 0. And that the row has to change because the element 5 also has to be a 0. So now, we're going to use, right, so I'm going to multiply negative 2 times row 1 and add it to row 2. I'm going to multiply negative 5 times row 1 and add it to row 3. And here's my work. So step 1, right, A and B parts, right? So this is part A and part B. So negative 2 row 1 plus row 2, right? So this will give us negative 2 row 1 is going to give us negative 2, 0, negative 2, negative 2, 0, and 0. Add it to row 2, we just bring row 2 over. We execute the operation. So we get 0, negative 2, negative 3, negative 2, 1, 0. So that's my new row 2. Now, the second step for row 1, right? I'm going to multiply negative 5 row 1. So it's going to be negative 5 times row 1, which will just bring it down. After I do the operation, it's going to give us negative 5, 0, negative 5, negative 5, 0, and 0. Plus row 3, right? So row 3, all we did was bring it down, the 5, 0, 0, 0, 0, 1. And then we do the operations. We got 0, 0, -5, -5, 0, and 1. So that's my new row 3. If we notice, right, if we notice here, for step 2, it's already done. Why? Because for step 2, these two must be zeros, right? And they're already done. They're already zeros. So we can skip. So row 2, I mean, we don't skip it, right? But row 2 is already done. So now we do step 3. So for step 3, right, we're going to use row 3. So the 1 must be a 0, and the -3 must be a 0. Right? We're going to keep row 3. So we're going to change row 1 and row 2. Here we go. Okay, so we're going to multiply. So it's going to be like this, right? So it's going to be row 3 plus 5, row 1, right? Because 5 times row 1 is going to give us a 5 here, and 5 plus -5 will give us a 0. But for the second for part B, we have -3 and -5, right? So they're both negative. So one has to be multiplied by a negative. So I'm going to multiply -3, row 3, and add it to 5, row 2. And here's my work. Row 3, right? This is row 3, right? We just bring it over. Row 3 is 0, 0, -5, -5, 0, 1. And we're going to add it to 5, row 1. So 5, row 1, we have 5 times row 1. Row 1 is 1, 0, 1, 1, 0, 0. After I distribute, right, it's going to be 5, 0, 5, 5, 0, 0. Then we add them. So this is my result. So this is my new row 1. Now, for the second part, I'm going to multiply -3 times row 3, right? So -3 times row 3, it will give us 0, 0, -0, 0, 15, 15, 0, -3. And then I'm going to add it to 5, row 2. So I'm going to multiply 5 times row 2, which will give us 0, -10, -15, -10, 5, and 0, right? So after we do the operation, it's going to give us 0, -10, 0, 5, 5, -3. That's my new row 2. If you notice, right, we're all done. These are zeros, those two are zeros, and these are zeros too, but one thing's missing. These must be ones. Okay? So I'm going to multiply row 1, right? So it has to be a 1. There has to be a 1 on the second row, second column, and also on the third row, third column. Those must be 1. So I'm going to multiply 1/5 times row 1. Right? After I do that, so 1/5 times 5 will give us 1. 1/5 times 0 will give us 0. 1/5 times 0. So all these will be zeros, and 1/5 times 1 will give us 1/5. Now I'm going to multiply -1/10 times row 2. So after I multiply -10 times every element, this is my result. In a similar manner, right, I need to multiply -1/5 times row 3 because we want to make that a 1. So after I execute the operation, it's going to give us 0, 0, 1, 1, 0, -5. So guess what, guys? Let me go back real quick. This is my inverse. 0, 0, 1/5, -1/2, -1/2, 3/10, and 1, 0, -1/5. So this is my inverse. I believe we're done with this workshop. Hopefully, this was very helpful. Okay. So let me go back. Let me go back to the to Blackboard. And hey, students, does anybody have any questions that I can answer for you guys?
Yes, sir, Mr. Zassi. It looks like Antonio would like to know how he can get a hold of that PowerPoint.
Okay, perfect. Antonio, you know what, Antonio? I'm gonna put my Antonio and Nazo. Well, you know what, guys? Here's my email. Okay, I'm gonna put my email in the chat. Okay, you guys send me an email if you want right now, and I'll send you the PowerPoint.
Awesome. Thank you so much, Mr. Zassi. At this time, does anyone have any questions for Mr. Zassi? Alrighty. Well, it looks like that PowerPoint will be awesome for them. Your audience would like to wish you a good day. I thought that was awesome. Okay, so anyway, I'd like to thank Mr. Azasi for presenting for us. Jesus has a question. He says he just sends you a message, Mr. Azasi.
Yeah. No, just send me. Just say this is Jesus from your presentation from your workshop. Could you please send me the PowerPoint, and I'll send it to you right now. And if you
Okay.
want, Jesus, if you want other PowerPoints from different weeks, just tell me something like, Mr. Sassi, could you send me all of them, and I'll be more than happy to send you everything that I have that I presented. Okay, but if you only want this one, just say that I just want this presentation that you did for week 10, and I'll do whatever you guys want. Okay.
That's awesome, Mr. Azasi. Also, in the chat, I'm going to post the YouTube playlist for Tohono Virtual Events. You can go back past this semester and watch Mr. Azasi as he goes over those PowerPoints as well. They say you're an amazing teacher, and they say thank you. So thank you, Mr. Azasi, for presenting for us today.
You guys are welcome, and have a wonderful day.
Yes, thank you. I hope you guys have a wonderful weekend. But before I let you go, I'd like to invite you to next week's session on November 4th. For Math 1314, we'll be going over linear and nonlinear systems. For Math 1324, we're going to be going over the exam review 3. For the 1 o'clock session for student success topics, we'll be going over the ATC Transportation Training Center and other ATC programs here at Vaiveve campus. So come and check it out if you're interested in that, and we hope you have a wonderful weekend. Thank you so much for coming today.